Hello, everybody. I'm Vagnozzi from the University of Cambridge, and welcome to my talk. The organizers of the conference, whom I would like to thank for their invitation, have asked me to give a talk on possible solutions to the Hubble tension. And I'm sure we can all agree that despite many attempts, which we see every day in the literature, we do not yet have a compelling solution to the Hubble tension. So given this situation, I thought what I would do is a so-called Hubble autopsy. So I'll try to explain why we have not yet found a solution, what are the mistakes we keep making when trying to find such a solution, and what, in my opinion, is the way forward in this tension. So in order to perform such a Hubble autopsy, I will have to start with a few important disclaimers. I will have to mention specific models and mistakes which appear in the literature. So I hope you will accept my apologies if your model or your favorite model comes up. And I will do this in a way which does not violate the conference's code of conduct. I will also assume that Adam Rees's local measurements are correct, and only insofar as they set a harder task for theorists. And I'm going to finally assume that you know most of the background relevant to understand this talk. So that being said, I'm sure we all know why we're here. The reason is this big mismatch between indirect and direct measurements of the Hubble constant, which you can also pictorially see in this nice drawing by Adam, where you can see this mismatch between the Hubble constant determined by the early root or by the late root. So just a quick review of how we actually measure H0 from these two different roots. In the case of the early root, if you look at a CMB, you can assume that you can treat the CMB as a self-calibrated standard ruler. Self-calibrated in the sense that the CMB can internally determine the physical baryon fraction, omega b h squared, from the relative height of the odd and even peaks. And that's essentially the feature you are using as a standard ruler, the sound horizon at recombination. Once you measure that, you can then use the inferred angular size of the sound horizon to measure the distance to the CMB, from which you get H0. And from both Planck and ACT-DR4, we get H0 in the high 70s, somewhere around 67 kilometers per second per megaparsec. I'm not going to mention these units in the rest of my talk. On the other hand, you can proceed via the local distance ladder approach, where essentially what you need is to have some calibrator, such as Cepheids or tip of the red giant branch, for which you can calibrate, for example, the period luminosity relation for Cepheids. And you can use these calibrators to move into the Hubble flow and actually measure the distance redshift relation of supernovae, which, if calibrated, can give you the Hubble constant. And this method, at least in the case of Cepheid as calibrators, gives you a Hubble constant in the low 70s, around 74. And the mismatch between the CMB and the local Hubble constant is at the 5 sigma level at this point, so it's impossible to ignore. So you might have noticed that I've so far not mentioned BAO measurements or uncalibrated supernovae. They are extremely important, and I'll get back to them in a second. Okay, so there are many proposed models trying to solve the Hubble tension. This is a slide I stole from Lloyd Knox, which shows that many of these models are either unlikely or disfavored by other probes. And in the rest of my talk, I'll go through at least some of these categories and argue why they are indeed unlikely. Okay, so what's the name of the game here? Can we try to find some extension beyond lambda CDM, which accommodates a high Hubble constant? And let's take a very naive zeroth order approach, looking at the CMB versus the local measurements alone. Now, this is a table from the Planck paper. You clearly see that there's no obvious extension so far, which can accommodate a higher H0 from the CMB alone. In fact, in many cases, H0 actually becomes lower. And if the tension is alleviated, it's only alleviated by virtue of larger error bars. So that's something which is hardly satisfactory. So we can take a next step. And essentially what we do is, let's look for some new physics, okay, such that in order to maintain the same acoustic angular scale as observed in Planck, we need a higher H0. And you can think of two classes of new physics which can do this. One class is early universe new physics, which comes into play prior to recombination and essentially affects the sound horizon RS. And one prototype is extra relativistic degrees of freedom, or an effective greater than 3.046. And you can also think of late universe new physics, which comes into play after recombination and affects the distance to the CMB. And the prototype of this is phantom dark energy, for example, with an equation of state less than -1. Now, I'm going to argue later that early universe new physics is much more motivated and likely to solve the Hubble tension. However, you might ask me, okay, what about late universe new physics? There are many models out there on the archive every day. What about this? In fact, there are many models with late time modifications which can give you a high H0 from the CMB alone. Okay, alone is the key word here. This includes, for example, phantom dark energy, interacting dark energy, decaying dark matter, phase transitions in your gravitational theory or in the vacuum, and so on. There are many, many, many examples. What is the problem? The moment you introduce late time modifications to lambda CDM, you have to take into account data other than the CMB. Because usually what these modifications do is they worsen the geometrical degeneracy. And then it's crucial to add data which breaks the geometrical degeneracy. In fact, I want to make a very, maybe somewhat hard statement. Constraints on parameters beyond lambda CDM, which affect late time, the late time physics, are meaningless if they come from the CMB alone. For example, constraints on the dark energy equation of state from the CMB alone are, in my opinion, totally meaningless. We need to include other data, such as the one I've shown here, BAO measurements, which constrain distances and expansion rates in the late universe, Hubble flow uncalibrated supernovae, which constrain the shape of the expansion rate, or even cosmic chronometers. And once you include this data, there's very little room for deviations from lambda CDM at late times. You can see this through the inverse distance ladder approach, where you combine BAO and uncalibrated supernovae. And what you can do is either calibrate BAO with a prior on the sound horizon from Planck, and then you see that you find a low Hubble constant, or you can play the reverse game and say, I'm going to calibrate my BAO with the local H0 measurement and infer the sound horizon. And then you see that you need a low sound horizon, lower than what is inferred within lambda CDM. So de facto, the takeaway message is that the inverse distance ladder obtained combining BAO, uncalibrated Hubble flow supernovae, and eventually cosmic chronometers exclude late time new physics as a solution to the Hubble tension. And if you look at this problem in the Hubble constant versus sound horizon plane, it's clear that in order to match all the available data, in this case, the local measurements, BAO, and the CMB, you need to reduce the sound horizon by about 7%. So you need to get to the X spot in the plot. Okay, but we are cosmologists, we are stubborn, and some of us maybe don't want to give up on late time solutions yet. And this is certainly a valid thing to do. And so what approaches can you take? I classify these approaches in 3 ways. One I call super naive, one which I call stubborn or head first, and one which in my opinion is more clever. And I'm going to cover this now. Okay, what's the super naive approach, which luckily no one has been following so far? You can argue that, okay, my uncalibrated supernovae go only down to a certain redshift. So in principle, I can imagine some drastic change below a redshift of 0.1, like a sudden speed up in the expansion rate, which brings H0 up to the reset R value. The problem why this doesn't work is that the true source of the tension is a roughly 0.2 calibration offset in the supernova absolute calibration between calibrated supernovae and Hubble flow supernovae once you combine them with CMB and BAO data. And this calibration offset is not something you trivially resolve via a sudden boost in the expansion rate. Okay, and this is also the reason why certain works have argued that rather than using a local H0 prior, it's perhaps better to use a local prior on MB, the absolute supernova calibration, or even better, use a joint calibrator Hubble flow supernovae likelihood. The next approach is, okay, let's consider dark energy. We don't know what dark energy is. The simplest theoretical candidate, the cosmological constant, is also extremely fine-tuned. So let's try to play around with all even remotely credible modifications to dark energy, like its equation of state. Let's make it time varying. Let's throw in interactions with dark matter or whatnot, all at the same time. We played this game last year, and the best you can achieve when including late time data like BAO and supernovae is about H0 of 70 plus or minus 1, which is hardly a satisfactory solution to the Hubble tension. Another interesting approach was this carried out by Marco Raveri, and it's basically a reconstruction of the late time expansion in the so-called scalar Horndeski model, where the tensor speed excess is set to 0. And in this low redshift reconstruction with several degrees of freedom and also a high frequency oscillations in the expansion rate, a Hubble constant of about 70 is achieved even when including late time data. This is very interesting as a proof of principle that in principle, late time modifications might give you a high Hubble constant. From the model comparison point of view, this is totally disfavor compared to lambda CDM, especially due to the many extra degrees of freedom, which are not warranted by an improved fit to the data. There's an interesting model, which is the Parker vacuum metamorphosis model, and this is well motivated theoretically at least, which at face value gives you a high H0 from CMB, BAO, and Pantheon supernovae of about 74. So this at face value is, that's it, that's our solution to the Hubble tension. But the problem is this comes at the expense of a huge delta chi-square. Okay, so this is totally disfavor over lambda CDM from a model comparison standpoint, which is also what the authors clearly say in their paper. Okay, so this is only an apparent solution to the Hubble tension. And finally, I think there is a very interesting approach, which I think is the most clever one. And it's the following. Let's say that our local measurements of H0 are wrong because new physics has confused our supernova calibration. And one example is screen fit forces, which would impact differently depending on which rung of the distance ladder you're on. This in principle works, but the difficult part is that this model cannot explain why strong lensing measurements of H0, such as from Holy Cow, find a high H0. Of course, you always have your get out of jail free card, which is to claim there are systematics in Holy Cow, which might very well be. If you account, for example, for the mass sheet transform, then the value of H0 from Holy Cow goes down. But I think in principle, these models will have problems with explaining high values of H0 from local measurements other than the distance ladder. So the takeaway message is it's certainly good in the spirit of it's a good scientific practice not to give up yet on late time solutions to the Hubble tension, but these solutions are at the very least unlikely. So let's move on to look at early time solutions instead. So remember that the name of the game is to reduce the sound horizon by about 7%. So how can we do this? So if you look at how the sound horizon responds to changes in the expansion rate, you clearly see that you need to operate just before a combination. And one promising way, a very interesting way to do this is via a model known as early dark energy. What you essentially have is a scalar field, which is initially frozen due to Hubble friction. So you essentially have a sort of early cosmological constant. And then this field has to dilute faster than matter. So you need a potential which is deeper than quadratic. And there are many examples constructed even from semi-realistic particle physics models for early dark energy. Now, early dark energy does not come without problems. It requires quite a lot of fine-tuning of mass, initial conditions, and potential. It's hard to get early dark energy to appear and disappear at the right time. The main problem of interest for this conference, I think, is the difficulties early dark energy faces when confronted with large-scale structure data or weak lensing data. And early dark energy appears to conflict with these measurements. The reason is the following. At early times, your early dark energy component is going to suppress structure formation. Then in order to maintain a good fit to the CMB, you need a higher dark matter density to compensate for the early dark energy effects. But this higher dark matter density is going to show up in the large scale structure as an excess power on small scales. And it's going to raise sigma 8, worsening the tension with cosmic shear measurements. Now, there are caveats to the combination of CMB and large scale structure data in the case of early dark energy pertaining to possible tension in AS, the amplitude of the scalar power spectrum. And I invite you to look at these recent papers for more discussions. There are interesting attempts to get an early dark energy phase from modifications of gravity, for example, in the case of the couple Galileon. But in all these cases, as far as I know, it's hard to go beyond H0 of 70 without either including the local H0 prior, which I'll get back to later on why this is not so motivated, or spoiling the fit to late time data. And I think so far, there's been no compelling model based on modified gravity to get an early dark energy phase, which successfully solves the Hubble tension. Another interesting proposal detached from early dark energy is to consider exotic non-standard interactions among neutrinos. You can think of this as self-interactions between neutrinos mediated by a light vector or scalar. Then there's a complicated scenario where you basically eliminate or reduce the free-streaming induced phase shift. And in order to then match, to get the right acoustic scale, you need a combination of higher H0, higher N effective, and non-zero neutrino mass. This is interesting, and it got a lot of attention for a while. The problem is that this model runs into trouble with CMB polarization data. And essentially, if you include CMB polarization or do not include the local prior on H0, you fail to get a high Hubble constant. You get H0 in the ballpark of 67 or 68, so no better than lambda CDM, as a matter of fact. Now, this issue of early models going in trouble with polarization data, in fact, is probably quite general. Because you see, if you focus on the blue kernel, that's the response of the damping scale to changes in the expansion rate, depending on your scale factor decade. Now, new physics, which is going to operate in such a way as to reduce the sound horizon, is going to affect the damping scale. Sorry, that's the orange kernel as well. And it's going to affect it by a huge amount. And in fact, the general message here is that it's very hard to reduce the sound horizon and at the same time not modify the damping scale, which is going to lead to undesirable effects in small-scale polarization data. There are many other independent early time approaches to solving the Hubble tension. I think all of them are unlikely, with the possible exception of the primordial magnetic field model studied recently. So the takeaway message from this part of the talk is that, yes, in principle, early time solutions are the most motivated solutions to the Hubble tension, but they face as many difficulties, if not more, than late time solutions, okay? And which is the reason why we haven't found a compelling solution to the Hubble tension yet, even from early time approaches. In fact, there's been a recent interesting paper which argues that reducing the sound horizon alone is never going to be enough to solve the Hubble tension. And this is essentially a generalization of the problems of early dark energy. So what happens is, if you reduce the sound horizon operating at a high physical matter density, you run in tension with weak lensing and large-scale structure data as early dark energy. But if you do that at a lower physical matter density, you run into trouble with BAO data, So it looks like it's hard to accommodate all data at the same time, and something has to give, very likely. The only caveat is that this analysis is done at the background level, and you can, of course, introduce new physics which only affects the perturbations, such as the neutrino non-standard interactions, which can bypass this conclusion, okay? With the caveat that these models are probably in tension with polarization data. So I think I've convinced you that it's extremely hard to fit all available precision cosmological data. If you want to think of this mathematically, it's like having an over-constrained algebraic system, okay? You cannot fit all the constraints at the same time. And fixing a problem somewhere makes a problem pop up elsewhere. And this reminds me of this game called Whack-A-Mole, where essentially you have to kill moles, but then once you kill a mole, other moles appear elsewhere in the game, and you never can win. And I hope this is not the case for the Hubble tension. One problem I often see in the literature is a questionable use of the local H0 prior. So many analyses simply threw in the local H0 prior, which of course is going to make the inferred value of H0 within your model higher, even if your model doesn't solve the Hubble tension a priori. Another problem I often see is that the tension is often relaxed or alleviated just because of larger uncertainties, with the central value of H0 not even necessarily going up, okay? Now, these two issues, I'm pretty sure we can all agree they are highly unsatisfactory. And regarding the questionable use of the local H0 prior, I wrote about this, for those of you who follow my blog, I wrote about it last year, making an everyday life analogy, which goes as the following. Imagine we are in a world which is the opposite of what we live in, where if you are rich enough, you don't pay taxes, okay? And this is sort of the same thing here. Imagine that not paying taxes is like being able to use the local H0 prior. Then being rich instead is having a high H0 from your CMB, BAO, and supernovae dataset combination. So basically, if you get a high enough H0 from the inverse distance ladder dataset, then you are allowed to not pay taxes and use your local H0 prior, okay, and raise your H0 even more. But if you don't get up to this threshold, you cannot include the local H0 prior. And I think it's fair to say that no model so far has made it up to this threshold. So the use of the H0 prior in many models has been questionable, at least in my opinion. So finally, let me address one question that many theorists have often asked me. What if I have a model, a particle physics or modified gravity model, which predicts a specific value for some beyond lambda CDM parameter, such as, for example, W or an effective? And in this case, it's like you have one less parameter, and your error bars, of course, do not blow up. Okay, your error bar remain as large as the error bar you get in lambda CDM for H0. The question then is there some sweet spot where the tension is reduced, the H0 tension is reduced enough, and at the same time your model does not give a horrible fit to either the inverse distance ladder or polarization data, so it's not too disfavor over lambda CDM. And as you can see from these plots, this is never the case. There's no sweet spot where you achieve this balance between reduction in tension and goodness of fit. And while I studied this only for W and N effective, I'm pretty confident this is true for many other extended models as well. So I'm coming to the end of my talk. I think it's time to summarize what, in my opinion, are the problems and common mistakes in the literature in attempts to solve the Hubble tension. And as a disclaimer, we are all sinners, including myself. We have all made these mistakes at some point. That's perfectly fine. The important thing is to try and not perpetrate these mistakes in future works. The most basic mistake one can make is to leave out a key dataset, such as BAO, Pantheon supernovae, or polarization. Then there's this issue I discussed about misuse of the local Hubble prior. There are models which claim to solve, in quotation marks, the tension just by inflating error bars, but not moving the central value much. That's clearly unsatisfactory. And finally, there are models which give you an apparent solution to the Hubble tension at the expense of either worsening other tensions with cosmic shear measurements, for example, or a poor delta chi-squared, which is not apparent if you only focus on H0. And finally, many models are very phenomenological, but are hard to incorporate within a compelling underlying particle physics or gravity model. So the takeaway message is that we don't yet have a compelling solution to the Hubble tension. Any claimed solution so far is overstated in the best case or wrong in the worst case. So what's my personal take on what's the road forward? So I think solving the Hubble tension will require a mix of early and late time physics. And I think it will require more late time than early physics. And I'm thinking, for example, of exotic effects such as back reaction of inhomogeneities, which can play a very important role. And this can also potentially invalidate assumptions in the BAO reduction process, such as assumptions on the Alcock-Paczynski scaling. And for this reason, I think it's important to get BAO experts in the discussion to understand really how important this measurement, how model independent these measurements are. Finally, I think there's also something interesting in the holy cow trend of the value of H0 you infer versus redshift of the lens. There's this linear trend, I'm sure many of you have seen, and I think there's something in there worth investigating further. And it's also important to focus on quantities beyond just H0 and the sound horizon, like the age of the universe. And this was recently advocated in a very nice paper by Bernal et al. In the context of cosmic triangles, as you see below. So I'm optimistic. I think we will get to the bottom of this in the next 5 years, after we solve the pandemic, of course. And whatever we learn will teach us something very fundamental, I think, about physics. So I'm going to leave you with what I define my 10 commandments for Hubble hunters. So of course, these commandments are meant to address the mistakes I've outlined so far. So of course, one should not fail to include key data like BAO, supernovae, or polarization data. One should not include a local H0 prior in vain, and try not to just blow up the uncertainties on H0, but keep an eye on its central value and Bayesian evidence or whatever model comparison tool you have. Try not to worsen other tensions, but rather try to explain them at the same time. And ideally have a model which comes from a compelling particle physics or gravitational construction, which makes verifiable predictions, which hopefully get verified. And I want to close with a quote from Robert Schuller, which I think is very relevant to the Hubble tension, which I think is not a problem, but it's really a guideline for what lies beyond lambda CDM, if we are able to indeed find a solution. So that being said, I realize my talk might have been, I hope it did not come across as aggressive. And I think it's normal that I will get criticism and comments. I'm very happy to take your criticism, especially if I mention your specific model or your favorite model. And that being said, I very much look forward to the discussion session of the conference. And I thank the organizers again for their invitation. Bye.